Hello friends, how are you all today? Have you ever wondered what operating system is and how it is going to work? It's coming up right now. I'm Prashant, a technical trainer and freelancer from Dharani Academy of Technical Education, Bengaluru. Let's start with the concepts of operating systems.
So we were looking at what is called as a monitor, right? Okay. So in monitor, basically we were trying to look at the solution of uh, programmer errors made by the programmers who want to use the semaphores. Whenever they use a semaphore, we understood that, right? There are certain types of errors possible, such as, right, you call a signal first, then after critical section you call a wait. That's an error, because normally you have to call a wait first, then signal. Otherwise, you call either only signal functions twice, or you call wait function twice. Okay, so that also going to end up in what is called as a deadlock, and we saw in the final stage that if you omit either wait or signal, that is also going to result in what is called as a deadlock. So in order to overcome such issues, right, we discussed that monitors can be used, and monitor has the following syntax. The syntax of monitor is the general structure what we discussed yesterday as a last topic, right? So you have the keyword monitor followed by the monitor name. Then normally initially we have to specify the shared variables declarations. Whichever variables you want to use as a shared variable, you can declare over there, followed by the different user defined functions. We call it as a procedure. So p1, p2, p3, etc. we can write. Okay, so there are n number of procedures shown here, and at the end you are supposed to write what is called as a initialization of the code. Okay, so this was the syntax. Now we'll discuss further about the usage of the monitor. Okay, so to start with the usage, right, just now we saw that there is a specific type of representation of monitor, but when you use such a syntax of monitor, directly you cannot use it inside a program for any purpose. Okay, or where any process cannot use a monitor as it is. Okay, so we'll write one point: the general syntax of monitor cannot be used. It cannot be used as it is, right, uh, for any process. So okay, so any process you want, you cannot use it as it is. So if you use a procedure which is defined inside a monitor, right, the idea here is that, because see, you want to eliminate the concept of critical section, in the sense whenever somebody is using a variable, you want to make sure that that variable is not being accessed by anyone else. So what you do in case of a monitor is you define a procedure inside the monitor, and you also have defined several set of variables in the monitor. Okay, so uh, what is the range of, or what is the availability of the procedure and the variables is like this: whenever you define a procedure, within a monitor, they can access only those variables declared locally within the monitor. Okay, and only the formal parameters of what is defined inside the monitor they can use. This is the first rule which we are going to impose on monitors and the usage of monitors, so that even if while we use the monitor, if somebody uh, makes a mistake in the programming part of not defining the functions properly, right, still we try to overcome the problem of uh, the what you call as the accessing the common parameters. Okay, so let's write that point now. A procedure defined within a monitor can access only those variables, and we can actually include the parameters, and the parameters defined inside the monitor. So local variables of a monitor can be accessed only by the local procedures. This is the ultimate meaning of the sentence. Okay, now moving ahead, let us say that we declared a monitor, and when we declare monitor in this fashion, we should ensure that only one process at a time can be active within the monitor, because we defined several procedures inside this, right? At a given point of time, only one process, right, can be active. So one should ensure that it's the job of the programmer who is going to use this, right? One should ensure that only one process at a time can be active, right, within a monitor. So specifically, when we talk about the usage of monitors, right, the programmer does not need to code this synchronization constraint explicitly, right? In a sense, the monitor construct as defined using the procedure and the variables is not sufficiently powerful for modeling the synchronization schemes, for which we need to define additional synchronization parameters. So let's look at the schematic view, how a how a monitor is going to look like. Okay, we'll call this that part as what do you call, okay, we'll call it as a schematic view of a monitor. In a sense, we'll understand, right, how the data can be uh, accessed, and how the data is going to be shared, and what are the operations, and what is the initialization code, and how the entry queue looks like for the data that is entering or leaving this particular monitor. Okay, so let's write that now. So let's say that right here, say at the top portion I have shared data present, then say few of the operations also we try to define. Okay, and the last part is this. Okay, so the top is the shared data, then here we have a set of operations which we have defined, right? This is the procedures, we call it as operations. And the last part as defined, it is initialization. Initialization code. So what happens is whenever we try to define the shared data, right, the shared data may be going in or out. Let's show only one of them now. So it's maybe we'll consider that it is going out. Shared data, whatever has been used, is being used to transfer the data outside. So in that case, I'll just write outside arrow. It can be the arrow which is coming in also, because from the outside world we may need the data which is coming in or going out. So I'll just write it as entry or exit queue corresponding to the data. So when we look at the monitor is going to show the following four parts. One is a shared data, second one operations, third is initialization code, or the last one is the queue corresponding to the data which is either entering or going out. Okay, so now so we understood that one process is going to be active inside the monitor, and programmer has no need to do in terms of the coding. The programmer has nothing to do with the synchronization constraint. No need to specify that explicitly. Okay, but now the idea is that in order to make the monitor sufficiently powerful for modeling a specific synchronization mechanism, what are the changes we need? So general monitor we saw, but now we'll go for making this more powerful. Okay, that is in order to make a monitor sufficiently powerful sufficiently powerful for modeling uh, modeling any uh, we can say synchronization schemes, right? uh, we need to define the following additional mechanisms, right? So monitors are going to be defined in the way which we saw, right, in the general code. And then we saw a structure, right? These are the different parameters present over there. Now we are trying to learn how a programmer can use the monitor in such a way that synchronization can take place, right? So now what we do here, in order to make it powerful to handle any situation, we use another construct that is called as a condition. Okay, so we'll write these mechanisms are provided by, right, the construct name itself is called as condition. Condition, this is the name, okay, construct. Like a construct called monitor defines a monitor, now we define another construct that is called as a condition that provides, right, several conditions which uh, you can incorporate while using the synchronization schemes, right? Now the programmer, what a programmer needs to do is to write a synchronization scheme that can define one or more variables of type condition. This conditional type variable needs to be created by the program. So this is the job of a programmer to take care, but this is not like not complex or not uh, time consuming like writing the codes related to the semaphores. Okay, right. So what programmer has to do? So a programmer uh, who needs to write a synchronization scheme. Whoever wants to get a synchronization scheme uh, has to define uh, one or more variables of which type condition. This type of variables needs to be defined, like, so for example we can uh, define it like condition, like we used to call int, character, float, like that. We have a new data type coming up which is called as a condition. We can call x, y, etc. Now the only operations that you can uh, invoke on any given conditional variable, right, we can actually call only two functions. Now I have two variables, one is x, one is y. On these x and y variables you can always call only two functions. I cannot call this, I cannot pass this variables x and y to any function, not at all possible, but only two functions you can try. So what are they? We know them. One is wait, one is signal, right? Now so the only operations that can be invoked on a conditional variable, on a condition type of variable are we can use wait, and also we can use the signal. Wait and signal. So how to call it? Now we slightly modify the calling functions, right? So let's write that here. For example, if you say this is x dot, we use a dot operator, x dot wait. So this means the process invoking this operation is suspended until another process invokes, right, the signal operation. Okay, so x dot wait. So let me write that. This means uh, the whichever process is actually invoking the wait signal, right? The process invoking this operation, I'll write this operation indicating that the wait operation is suspended until some other process actually calls the signal operation. Okay, until some other process invokes a x dot signal operation. So we know that if you use a x as a variable, x dot wait and x dot signal are the two operations. So the x dot signal, whatever we have written here, it's an operation resumes the exactly one which is suspended the process. Okay, only one process can be resumed through a x dot signal operation. So the idea here is that if you call x dot signal, so we will be writing it in such a way that, right, this resumes only one process, not multiple processes. If at all multiple processes do exist, right, only one will be activated, others will be still in the waiting part. Okay, so this is an operation which resumes only uh, only one suspended process. So if no process is suspended, then the signal operation has no effect at all. Okay, so the state of this x is the same as the operation which has never been executed. So when it was not executed, we'll see that there will be a state related to a particular what you call monitor having several conditional variables. Okay, now let's include the what you call as x and y conditions in the monitors diagram. So that's going to look like this, right? So I'll write monitor with conditional variables. Okay, for that I need to, okay, we'll copy this and we'll paste so that this is okay. Now this shared data part what we have here, right? So this will be uh, okay, let me erase this part. So in this shared data part, we are going to have say maybe it's like a queue, one corresponding to the x. It can have n number of spaces available uh, in the array. Y can also have some number of elements over here. Okay, all together we have the shared data. Only that's the change. Other than that, remaining part of the code will remain same. remaining part of the diagram is going to remain same. So this is actually the queues associated with X and Y conditions are shown here. So I'll just write that part. So whatever you are writing here is corresponding to the queues associated with X comma Y conditions. Okay, right. Now if you recall the signal operation that we discussed in the semaphore, right, the state of the semaphore will be changed whenever you call a signal. But now we understood that the signal operation, if the signal operation is called here, right, resumes the one which is suspended process, and if there is no suspended process, nothing will happen. Okay, no change. But if you recall, the signal was actually incrementing the semaphore's value, whatever was present was getting incremented in the semaphore section. But now you see in monitor, if there is no suspended process, means no change. Okay, so that's the important part that comes into picture when we discuss this. Okay, we'll make note of that when we go to the coding part. Okay, now let's go ahead. Now let's assume that the X dot signal operation is invoked by a particular process. Okay, so let a process, we call it as a P, a particular process P uh, invokes the X dot signal operation. Okay, so it means associated with this, whenever you call this particular signal associated with the X variable, there is a suspended process Q. This is assumption. Okay, just to understand the process, we are going to assume like this. So there is a process P which invokes X dot signal. Okay, and say, and there is a suspended process. Already there is a suspended process, and let's denote it as Q, and this is associated with okay, I want to write the condition associated with the condition, say X. So if the suspended process Q is allowed to resume its execution, right, the signaling process P must wait now, because P actually has called the signal function. So now P cannot proceed, Q can be allowed, right? This is one thing. Otherwise, both P and Q would be active simultaneously within this monitor, right? So we have to take care that so both processes can conceptually continue with their execution, as we understand that okay, both can, because P was the one which now intimated that Q can continue. But what happens to P, right, we need to understand. So there are actually two possibilities with this, we'll see. So now we'll discuss that point now. So if say the Q is allowed to resume its execution, then there are two possibilities. Okay, what are the possibilities? The possibility number one is, first thing we called as signal and wait. So in signal and wait, P either waits until Q leaves the monitor or waits for another condition to appear. Okay, so this is the first part, that's called as signal and wait. So here P uh, either waits, okay, we can write until the Q leaves, in the sense finishes its execution, leaves the monitor, first thing. Okay, or waits for another condition. This is the first thing. And the second option, the second possibility is called as signal and continue. So in this case, now we talk about Q. So Q either waits, because P is going to continue now. P will not stop. P will just say that give a signal and it will continue. So when P continues, Q has to wait. So Q either waits until P leaves the monitor, or right, it actually waits for another condition to come. Right, so what exactly happens, right? Either of the options could be true, right? Since we know that the P was already executing inside the monitor, the signal and continue method looks more suitable, because it's already executing, means all the variables associated with the P is already occupying the processor, right? If at all you go for the signal and wait procedure, then P has to vacate all the occupied memory, and the same memory needs to be loaded with the variables associated with the Q, which is going to take some time. So signal and wait may not look very familiar for us, because everything needs to be rescheduled, right? But signal and continue looks very suitable for us. Okay, so that's something, it's also called maybe you can call it as a reasonable idea, that P already has loaded, allow it to finish, then the Q can come. Okay, uh, there is called as another view of this same thing, right? When if a question comes, when you answer, you can actually explain this. If at all you allow the P to continue, uh, P will finish after some time. By the time Q resumes, right, there will be a logic condition for which Q was waiting, right, is no longer hold, correct? Because see, depending on some condition you are executing, right? Now if at all Q needs a condition to be true, only under that case it can actually resume. But if you make sure that signal and continue is given for P will take some time to finish, but by the time Q starts, the condition which Q requires may not be there, right? So those are the two aspects of the possibilities which you can choose. Okay, this is, again, the monitors are used very widely and it's a very in-depth concept, but your all the textbooks what we are referring to, they are not going in that much depth. Okay, so until here is the concept of monitors. Now we'll see how this can be used in a dining philosopher's problem, right? How we can solve. So we'll try to solve the dining philosopher's problem using a monitor. Okay, just to make sure that okay, this is a valid synchronization scheme. All right, so that is uh, solution to dining philosophers using monitors. Okay, so the idea here is that we had a solution for dining philosophers problem using semaphores, but there was a very clear idea that if every philosopher tries to pick up one chopstick, it means that there is a deadlock. Now the idea is that using monitors we have to provide a deadlock free solution. Okay, you can put some restrictions, no issues, but when everybody is trying to do the same job, there should not be a deadlock. That's our condition. Okay, definitely without imposing any restrictions it's not possible, because there are five philosophers trying to eat something. Okay, fine. Now what solution, what is a restriction? Let's try to start with the restriction here itself. Okay, so that it becomes easy for us in the next stage. Okay, uh, so using a restriction, it uses a restriction that a philosopher may pick up the chopsticks only if both of them are available. In the sense, first you need to check whether both of them are available, then you can pick one of them one by one, definitely. So because picking up is one process, dropping back is another process, so you call one by one. But just to make sure that you can pick up, you need to check that whether they are available or not. So in order to write a code for this particular solution, we define and distinguish three states, okay, in which you can find out uh, you can actually you can find out what are the three possible states of a philosopher. Okay, so let the states let the three states associated with any philosopher be. So what we do, we use a data structure for that. Let's call it as a maybe you can call it as a enumerated data type, enum, right? Use a curly bracket. First state you call as thinking. It can be thinking, or maybe hungry. Hungry in the sense just a state which is before picking up a chopstick, and the third state should be eating. So out of which maybe the hungry state is going to be the waiting state. Okay, where you are hungry but you are not getting a chopstick. All right. So then okay, after this we are actually writing. I'll slightly move to right. It's the same line. So eating, after that I need to define state. So this is state enumerated data type of size 5. Okay, so that's how we define this. Now, under this condition, any philosopher, say philosopher I, can set a variable state of I equal to eating or equal to thinking equal to hungry. But now the eating state can come only if both the neighbors of that particular uh, philosopher is not in the state eating. Okay, this is because, right, when your neighbors are not eating, then only you can have two chopsticks available. Correct? So just to make sure that we are using this. So a philosopher, say I, a philosopher I uh, can set state of I equals to eating. That is the state only right, uh, if the neighbors are not eating, indicating that chopsticks are free. So how do you find out? How do you find out whether the neighbor is not eating? How to verify? So what is the condition to be checked? This implies, right? I'm supposed to check the following, right? The state, I can write, you see, I plus 4. What is I plus 4? I plus 4 is your previous one. Okay, I plus 4 mod 5, right? This state is not eating, not equal to eating. This is my first condition, indicating I'm checking that whether my previous philosopher is eating or not. It should be not eating. And I have another condition to be checked. That's my next person. So that is state of, this is simply I plus 1, but take a mod 5. Okay, that's also is not equal to eating. I need to check this condition, right? So that, right, I can define my state as eating state. Okay, so what we discussed, we try to write as a condition for code. We'll write a code later. Okay, that's first thing. And in the next part of the code, we will be using a condition, because conditional variables are what we just saw in the monitor part. So since we are using the monitors over here, right, we declare the condition. Okay, this is condition. It's a type of the variable. We call the name of the variable as a self. In a sense, everyone's self conditions. Again, I'm going to declare 5 such. It's an array of 5 elements, right? Using this condition, any philosopher can delay, right, when a philosopher is hungry but unable to obtain the chopsticks. Okay, so right here, ith philosopher uh, can delay the eating process when hungry but no chopsticks, sticks available. In the sense, neighbors are eating. Okay, fine. So going ahead with the solution part. Now we can describe our solution of this dining philosopher's problem. So this is how the distribution happens. So we know that whenever the chopsticks are present, they are distributed, and the distribution is controlled by, say, one monitor. Let's say, let's call it as a, maybe by some name, maybe DP. Okay, so already we have defined that, but anyway, let's define the monitor now. Okay, so let's first define the monitor so that this becomes easy. Okay, say the distribution of say the chopsticks, distribution of the chopsticks is controlled by a monitor called DP. It's a name, right? Let's try to define the monitor now. So monitor DP. Okay, define enumerated data type. So the possible states: thinking, hungry, eating, state of 5 such states. Right, then we need the condition self, that's also 5. So you see that this is the variable declaration part. Now what exactly you require? We have to write inside any monitor, we need to write several procedures. Okay, what are the different procedures we can write inside this monitor DB? One is for picking up, one for you're going to put down the chopstick, picking up the chopstick, second one, and the third one could be the testing the state of your neighbors. Correct? Okay, so let's write that. This is void, right? This is pick up is the name that we are going to give. I'm going to pass an integer I to this. Okay, so the state of this I is equal to hungry, right? Then I call test I. I'm going to write the function test later, but you see that I'm using the variables and the values present inside this monitor only. Okay, then I check a condition. So if, right, the state of I is not equal to eating, right, what I'm going to do, I'm going to call the waiting part. So I'll call the wait function, that is the self I. This is like x dot wait. All right, so I close my pickup function over here. So you see that this means it is picking up the chopstick and it's calling the wait function now, saying that others have to wait. In the sense, its neighbors should wait now because it's eating. That's the first part. Then let's go to the next function that we are going to write here. That is void put down. Again, pass integer I to this. Okay, when you call this put down, right, what happens to the state now? It's not hungry, it is not eating, it will go to the state thinking, right? So we just have to make that change. So this is state of I is equal to thinking, and you need to make sure that this is informed to your neighbors. So you call it as a test. uh, this is I plus 4 mod 5. I call the testing of that. Also I call the test, this is I plus 1 mod 5. Okay, that is done. Then now we'll go for the actual testing part. Okay, so that is a void test int I. Okay, so what exactly happens inside test? First I'll check the condition. Okay, that is, we'll go for a if condition. If state of I plus uh, state of I plus 4 mod 5. Okay, this state is not equal to eating. I continue here, and I close this. There is an and condition, and so this is state of I equal to hungry. Okay, and another condition, and this is the next one, also not should not be eating. So that is also the state of I plus 1 mod 5 is not equal to eating. If this is the condition, right, you see three conditions we are checking. The previous philosopher is not eating, my next philosopher is also not eating, and I am hungry. These are the three conditions you are checking. If this is the case, then, right, I'll update. If this is the case, I update my state of I equals to eating. Update your state as eating, and right, call the signal part. So that is self I. This is like x dot signal. Okay, I close this and I close this. Right, that's the close of the testing function. So functions are clearly written. First part is for picking up, second is for to put down, and the third one is to test. Right, if the conditions are met, then you can eat. Okay, then we need actually the last part of the monitor, which is called as the initialization. Okay, so we'll write that part now. So this is initialization code. So this is what is the initial condition? Everybody is thinking. Okay, that's the initialized condition. How can you make that? So we'll put a for. So this is int I is equal to 0, I less than 5, I plus plus. Right, I'll just write the state of I equal to thinking. We assume that initially everybody is thinking. You make sure that nobody is hungry or eating at the beginning. If you make everybody eating, that means that's wrong, right? Okay, so this is the closing of initialization code, and we close, yeah, okay, monitor which was opened over there, we'll close it here. Alright, so what we can discuss about this, it's very straightforward. Uh, Once we understand this code using the monitor, it's very clear that this solution ensures no two neighbors are eating simultaneously. Right? That's a very important point which we need to uh, talk about. Okay, so we'll write that part. This solution ensures that no two neighbors, no two neighbors uh, are eating simultaneously. This means what? No, no deadlock. So comparing the monitors with the semaphores, there was a possibility of deadlock. Now we try to overcome that, right? So there is no deadlock means there is no waiting, right? So none of the philosopher will starve to death. Previously we had a problem with that. Now we don't have that. Okay, so that's how the monitors can be used to solve the very important problem of dining philosophers. Okay,
That's all for today. Let's resume the concepts in the upcoming classes. If you have any doubts related to the topics we discussed, please feel free to contact me anytime. Thanks for watching. Have a nice day. Goodbye.